Thank you. Good luck.
We go. Okay. Works. Okay. Good afternoon, and thanks for the Sonic Foundation for organizing this workshop. It's always a pleasure to be here, learn about the latest innovation in Sonic, but also share with the Sonic community what we are doing with the operator in order to bring some new innovation in Sonic. My name is Ahmed Abdelsalam. I work as part of Cisco, and today I'm going to talk to you about some of the work that we have been doing with our colleagues at Alibaba in order to enable the topology visibility in Sonic. So this is a joint talk with my colleague from Alibaba, Joy, but unfortunately she could not be here today because she has a conflict, so I will be doing that talk on behalf of the Cisco and Alibaba team. Okay, so I'm pretty sure all of you know about the huge investment ongoing right now in AI in order to meet the requirement for the training demands. And we all understand that one of the key challenges is basically the power in order to power all of these different data centers. Basically, you cannot fit all of this infrastructure in a single data center. And the solution that everyone is doing is to spread this infrastructure across multiple data centers. But in order to in order to connect these different data centers, you need what is called AI DCI. And this DCI is basically needed to build that what is called like a supercomputer, or that large-scale infrastructure needed in order to to meet such training demands. This is something that has been explicitly explained in this blog from Microsoft when they announced their Fairwater DC for the need of AI WAN to build that supercomputer, but also has been explicitly mentioned in the latest announcement from Google about their Virgo scale-out network, where they explicitly explain the massive scale that is needed for that training demand, and basically that you cannot fit all of this infrastructure in a single data center, and you need to build a multi-data center. And again, the need for the AI DCI network and WAN is a key here. But let's look at this DCI and WAN network and what are the key, let's say, characteristics and the challenges that we have in this network. First, this network has to handle different types of traffic patterns, different requirements, RDMA versus storage traffic, but also traffic direction going east-west between the different data center, but also north-south going from the data center to the outside the world. And in this DCI network, typically your topology is less symmetric, or you don't have the full mesh nature of the leaf spine that you have inside the data center. Capacity is much more expensive, much more scarce there, so you don't have exactly the same capacity that you have in the network, so you need to handle these bandwidths and this capacity much more efficiently. Latency, we know that latency matters a lot in AI, and here when you have to cross a DCI network, you have to cross multiple hops, longer fibers, so all of this also is a key challenge in this network. But you also get a lot of, let's say, particular things like SRLG, or all of the, let's say, shortcuts that you need to do between the different data centers. And when you look at all of these characteristics, immediately you realize that there are two things that will be needed in those, or must in this network. Basically, traffic engineering in order to steer the traffic on the right path for the right, let's say, for the right requirement, but also fast reroute, or a mechanism to protect the traffic against failure that happen in the network. So if we look at the traffic engineering, basically you have different types of traffic, you have different characteristics for this traffic, they have different patterns, so you need to compute different passes in this network based on that minimize latency, for example, for the RDMA, where the latency matters a lot, but also you need to have different or meet different requirements like disjointness, when you need to have your backup pass completely, or your second pass completely disjoint from the primary pass for failure scenarios. Some bandwidth guarantee if you are sharing this network or sharing this infrastructure across multiple tenants or multiple customers or multiple data center, etc. And fast route is very well-known technology in IP. It is used basically to protect traffic in the network against all different types of failure: node failure, link failure, SRLG failure, etc., etc. And here it's well-known, deployed widely in the wide area network, basically with some techniques like loop-free alternate, LFA, where you compute your backup passes and you install them in advance, and you need just a quick trigger to enable the backup pass. But also TLFA, where you can protect this traffic in any kind of topology by steering traffic using some source routing technique, etc. And all of the techniques also that come with it, like micro loop avoidance, etc. So those are like kind of key characteristics that we need in those DCI network. And when you look at those characteristics, there is one common fundamental building block that you need in order to do all of this computation. You need to have a view of the topology in order to be able to do all of this computation. And when you look at the topology now in SONiC, or generally what we have seen is that you have many people try to do the topology in different ways. Some of these techniques, or many of them, they were non-standard, basically a bit fragmented. You try to collect as many telemetry as you can from the network, trying to build a view or a topology view of the network. And many times it's static, so for any dynamic failure or anything that happens in the network, you don't learn at least very quickly about this. And a lot of this topology collection, it was a bit bound to IGP. So conceptually, or I would say misconception, that if you need to have a topology view, you need an IGP protocol. But in SONiC, we typically run SONiC eBGP fabric, which is a hop-by-hop fabric. How we can also have the topology view in this network, where in an eBGP fabric, I have only a view about my neighbors. How can I have the full topology view? So the goal that we want to have in SONiC is basically to build a solution to have the topology view. This solution based on a standard, open, supported by multi-vendor, and also it scales well for all of these different deployment. And we want the same solution to work, either I run IGP, or in like most of the SONiC deployment where it runs only eBGP fabric. And then when you look, there is actually well-known method in the industry to do topology collection, which is called BGP-LS. And basically it was initially designed for IGP, so that's also how the misconception came at the beginning, that everyone thinks that when you use BGP-LS, you really need to have IGP in there. This is not needed, and you will see during the presentation that we can have the same topology views that you have in an IGP network via BGP-LS in an hop-by-hop eBGP fabric. It's something standard. And again, another thing that was commonly, that people typically think that in order to, or BGP-LS, its only job is to export the LSDP or the link state database. It's not direct export. It basically takes this information, normalize them, and send them in a standard or topology model. This topology model is typically made of 3 elements: nodes, links in the fabric, and also the prefix. But this topology model has been also extended extensively to include the segment routing information, the segment routing policies, etc., etc. And for each one of these objects, like the node or link, you have a new NLRI in the BGP link state address family. So why BGP-LS and why nothing else? Because why do we do something else different from the whole industry is doing? Is it standard? It's supported by most of the vendor. It's supported by open source stacks, and you will see during the presentation, we have contributed the support of BGP-LS, both for IGP fabric and BGP fabric, to the FRR. So it's already part of the FRR mainline, ready to be consumed, and it will come as part of the SONiC in the next FRR upgrade. It scales very well because basically we are not introducing, BGP-LS is not a new protocol, it's just a new address family in the BGP protocol. So it uses all of the scale infrastructure of BGP, including route reflectors, all of the policy filtering, etc., etc. And it can provide you a full topology view of multi-domain. And again, from application perspective, if you run a controller, you just need to have a session with that collector, and you get a full topology view just from a single location without having to do the collection from all the different parts of the network. And it's just purely control plane. There is no impact at all on the data plane. Let's see how BGP-LS works in the IGP network and how we export this information and how it is supported now in FRR. And then we will see how the same model, exactly the same information we can get from an eBGP fabric and with the same representation. In an IGP network, what happens is that all of the nodes participating in that IGP domain, they exchange the link state between each other. So what you get at the end, each node has a full view of the topology. What you need to do is that build or have a BGP session with any one of these nodes, and you get all of the topology information from that node. But remember that in order to have the topology information at each one of the nodes, this node has to exchange information between each other. How is it in FRR right now? So this is something that has been part already of the FRR mainline. We contributed this couple of months ago. And basically, in ISIS, when you do the configuration of ISIS, you just need to enable the distribution of the link state information with that command that you see here, distribute link state. And then you have your BGP session between one of the nodes to the route reflector, and it's just a new address family in the BGP protocol. So you are already running BGP, you just need to have this new address, you enable this new address family, and all of this information that you see here is going to be sent to the route reflector. What are the information that you have as part of this different LRI? You have a lot of information. So basically, it gives you very rich topology that may be more than you need, but actually it has everything that you need, even more than this. So you can see all of the attributes that you have for a given link, for a given node, or for a given prefix. Now, and as part of the FRR, we have some debug CLI if you want to look at all of this information in FRR. Now let's go to the part which is likely more interesting for the SONiC community, because we all run eBGP hop-by-hop fabric. How can I use BGP-LS in this network in order to get the same topology information that we just saw in IGP? So eBGP is the norm here. It's used in the data center. You use it both for underlay and overlay, and also it extends naturally. The minute you want to take SONiC from the data center and you put it in the DCI, you build these DCI networks also with eBGP fabric. So you use the same tool set, same operating system, same experience, etc. And to remind, in order to get a topology, there is no need really for IGP. You can do the same with BGP-LS, and this is not something that we recently introduced. It's something that has been in standardization for IETF for some time, and there is already an IETF draft. It's a working group draft to explain how you can export the link state information in an eBGP-only fabric. It is already also has been also merged in the FRR mainline, so it's already available. And from your controller viewpoint, if you have a controller that used to get the BGP-LS topology from an IGP domain, it can exactly get the same information or from that eBGP, so there is no need to change anything in your application or controller, etc. So how does it work? Remember, in IGP, the nodes exchange information between each other in order to build the topology view. In eBGP, to me, it's actually even more simpler, because you don't have to exchange those information with everyone in the IGP domain. You just need to send your view of the topology to that route reflector, and he's going to put all of this information together. So in IGP, what happened? Node 1 sent to everyone, here is, or every one of its neighbor, this is my link state information. It's not going to send it to its neighbor, it's just going to send it to the controller. Node 2 is going to do the same, and we already all of these devices are running BGPs. You just need to enable this new address family, which is the link state address family, with a peering session to that route reflector, and the route reflector is going to get what information is going to get. Is going to get a node NLRI from node 1, node 2, 3, 4, 5. Then the result, he has all of the node NLRIs for all of the different nodes. He's going to get all of the link information from each one of the nodes, and he's going to build exactly the same topology information as you get in IGP. So, and if you look at this, it's already part of FRR, as we mentioned. It's already merged in the mainline. How do you enable it? Again, just enable the address family under BGP, and you pair with this information, with just route reflector to send this information directly to the route reflector. So as a result, what you have here is a unified solution to get the topology information either from IGP or BGP exactly the same way, the exact same NLRI, the exact same information in the two networks. In IGP, the difference was that the nodes exchange information between each other to build a full topology view at each node. In eBGP, much simpler, you don't have to do that. You just send this information to that route reflector, and he will put all of this information together. So this BGP-LS, it's really, let's say, an essential foundational building block, because once you have it, you can do many things. We can do all of the traffic engineering capabilities that we need in this DCI network to compute the different set of passes, etc. You can do all of the fast reroute or the protection mechanism like LFA or TLFA, and this is something that we have recently submitted a draft to IETF to explain how would you compute fast reroute in an eBGP-only fabric. And the key essential component for this is basically the topology, but we have it already. And this also opened much more, let's say, room for innovation here, where once I have the topology, I can do all of the different analytics in terms of passes, topology changes, how my topology evolve over the time, and I can have all of these analytics dynamically. So to conclude, there is a huge investment in AI where we need to scale this infrastructure for the AI training demands. We need to build multiple data centers to fit all of this infrastructure. In order to connect them together, we need the AI DCI WAN. These networks have specific characteristics which require to have the capabilities for traffic engineering and fast reroute techniques. And one of the essential building blocks for this to achieve these capabilities is to have the topology. And now we have a unified solution for the topology, either in IGP or BGP, which is using BGP-LS. It's something standard and multi-vendor open, and we have it already supported in the FRR mainline. And with this, I advise or I invite all of the attendees to look at the code, basically test it, etc. We have some demos running with this. If you are interested, feel free to contact us. Thank you.
Just a quick question. Thanks for the presentation. You mentioned it's in FRR, but what about adding support in SONiC in terms of the Yang model and FRR CFGD? Is that in the plan, or is that part of your current already supported FRR?
Okay, so very good question. Many thanks. So the first step in order to enable that was to add the support in FRR, and that's, let's say, we closed that first step. And in order to get this fully integrated in SONiC, we need to look at all of, let's say, telemetry models, etc. that we need. So I think that will come as a next step. So, and we will be happy to collaborate on doing that. More questions?
It's on. Okay. So this LSRR, route reflector. It doesn't have to be a route reflector in the traditional sense that it reflecting other IBGP or BGP routes. It's just receiving the link state information. Is that correct?
Yeah, it can be, let's say, any BGP device in your own can be also your BGP route reflector. It just needs something that needs to pair with all of the different nodes to get this information.
All right, thank you.
Yeah.
Let me bring the mic here.
First of all, thanks for your presentation, very interesting. Two questions. The first one, any possibility to include more information in the protocol, right? For instance, let's say bandwidth or maybe latency of each link that is integrated in the database? First one. And the second one, any possibility to obtain the interlink information from, for instance, LLDP to populate the routes inside the BGP-LS?
Okay, so I'll take them one by one. So the first question regarding adding some of the metrics. So you mentioned, for example, in delay, and if you look at all of the attributes that you have in the BGP-LS, delay is already one part of those attributes. And the way BGP-LS work, basically you have this NLRI and you have some TLVs that are mandatory, you need to send them, but you have a bunch of, let's say, optional TLVs that you can already extend them and add other TLVs. So I think if there is more information that would be needed to be exported regarding the topology, if it's either available in one of the TLVs, we can support them, or we can extend the model to have new TLVs.
Then big applause.
Thank you.
And Ahmed,
No.
something to remember.
Thank you.
Hopefully came back.
Thank you very much.
Thank you.